Hello and welcome to this last video of this section. In this video, we'll be using natural logarithms to linearize nonlinear data and make them linear models so that we can apply equation of a straight line to harder problems. So, let's see. As I said, you can make a nonlinear graph like so into a linear graph like that. Now, in statistics, you won't get exactly exponential curves that or data that will fit exactly on the line, but they will be roughly close to a shape like that. If they are close to but not exactly on it, they can still use a logarithmic model and linearize that to get a graph like so. If it has a positive gradient there, you will have a positive gradient in a linear model. If it has a negative gradient in the exponential model, it will have a negative gradient in the linear model. So let's see how it's done in real life. So let's say y is this, it has this particular equation where t is power of b here. Those k and b are some coefficients there. So taking natural logarithm of both sides, now you know natural logarithm rules. You can say log of k b raised to the power of t means that the t can come and sit in front of this logarithm, and furthermore t will multiply by log of k. If we expand that, log of k plus log of b, and therefore t will multiply into that bracket and I will have equation here. Now, why did we exclude b there? So you have simply this equation here. So if we want to prove that it can be, you may not have it written for you, given to you. If you take log of both sides, you'll have log of y equals to log of k kbt. Now, using natural logarithm rules, first you can divide this into log of k plus log of b. Alright, and that power of t can come and sit at the front, and therefore now you have this situation. Now this plus sign here and this log of b. What it means is that this t is the variable in our class in this model. So variable, and that means that what is a constant is this. This is our gradient m, and this will be our intercept c. Now I'll show you this in a neater way somewhere further along on the next few slides, so don't panic. Here, graphs, I'm just showing you that if you have an exponential model and you take natural log of both sides, it will turn it into a linear line like so. So what would happen to this model if you have x squared plus 3? So taking log of both sides, you will have 2 log of x. What's the and the intercept would be then well now then it wouldn't king log of x squared plus 3 actually doesn't make a good model. And so here I'm just going to show you some graphs where when you take the log of both sides of this equation here, you end up with the equation on the right side of the page, written in blue. Log of y equals to 2 log of x, and that's when you actually turning the log of x here against the log of y. Notice that's why it's has a gradient of 2. Otherwise, it wouldn't have. Actually, well, yes, it does have a gradient of 2. 2 matches with 4. Okay, so now there are two versions of the models that you may be given. It very much depends on the context of the problem. You have no say in it. Just think about these two different models here. One version is this, another version is this. Okay, here x is in the power, but here x is a base and n is the power. So notice y is variable and x is a variable. Okay, here variables are so, here variables are here and here. So let's apply natural logarithms to both these equations. Let's start with 1 first, that model 1. When we take log of both sides, we break this up into log of a plus b log of b raised to the power x. We will bring the power down on the next line, and then we can see this as y equals mx plus c, where y would be log of y. Now notice here mx and here is this log of b, because we said this is a variable, and if x came down here and we didn't change it, is still a variable here. So what's a constant is log b. Log b is n, our gradient. Now we can find it with writing a different formula. We can use exponents and logarithms later. I'll show you how to do that. But you just have to match variables once you have taken a log, and you can say log of a is just a constant, my intercept c. Alright, so now coming down here and taking log of this equation 2. Let me get rid of the writing so it's not confusing you. And taking log of both sides, we break it up like so into two logs, and we bring the power down at the front. Now again, log of x this time is, these two are the variables, these red boxes. So what's the constant is that n, right? Their order doesn't matter. In the other case, a expression, I mean, is multiplied by x. Either you write xm or mx, x is unchanged and multiplied there. It makes that makes it the gradient. Now in this case, our gradient is this, because this is the variable. All right, I was trying to say that you need to isolate what's changing in our data. Datas are here. Each x point is representing the variable. So here we are matching, or rather graphing, log y against log x in this bottom left corner. There on the bottom right corner, we are, notice this log y will be graphed or plotted against x, where we didn't transform x with logarithms. So therefore its graph will have x in as the on the axis. So one of the clues when you deal with these models in this chapter and the first chapter of applied mathematics and statistics, and in year 13, is to look at the graph, and that's a clue for you. All right, which, so in this case we are saying that I'm just rewriting the y equals so you see that have to be at the end here. Here our m is log b, and x is, I've written it as little x, so that's not changed, but I've written with a capital X, so you know that something has changed from this line to this line. There's a transformation. It wouldn't make sense for me to put little x here, and here this y is transformed. Maybe I should have changed that to capital Y as well. All right, so now here's the first example. We've been told that we've got some rankings for the four or five cities and populations, and we are we've been told to use this model. All right. Addition is a times r raised to the power of n, and we don't. Uh, r is our variable, okay, and we're going to take log of this this functions that's got exponent of n there. We want to bring them down here. First of all, up here shows some sort of a negative exponential curve, and we can take log of both sides here. So I rearranged this equation for you at the beginning of the lesson. Remember, it gave us this line here. So we're going to do the same for this expression here. We are going to get log p equals to log of a plus n times log of r. Okay, so n comes and sits at the front. There, exactly there. So I'm gonna take this off, and now all we have to do is with the linearized version of this model. Okay, with the question saying draw the table of log a and log r and log p, because that was in our equation. Notice equation for you, we had log p equals to log a plus n log r. So we do need to transform log r and log p. That's why in this case you can use the table menu on your calculator. You don't have to sit there and take log of each of those numbers there. You can put them into a table and the function log, write a function log, and it will give you that. So I'll make sure I make a video for you there how to use a calculator if you don't know the table menu. So once you got these, when we plot the red values, these red values are plotted on this graph here, and you see that they much easier match a linear line. Okay, they make a linear model there. So therefore, we can use that linear model to the intercept and what's the gradient. And I've just written the same thing that I wrote previously. This line here, I've put it there. I've just written them so it matches nicely with uh, y equals mxc. This is a skill you need to learn to do yourself. I can't come and do this for you. It's just rewriting variables in the order that you would read them. Uh, so this case n is our gradient. What's changing is log r on the x-axis. So we're plotting log r down there. So you take any of, notice I'm taking this red table that we calculated. This is not the original data. So this is not the original one. This is a transformed data. Okay, transformed data. And we can take any two coordinates, calculate the gradient, just like we did in chapter 5, and we get a gradient of negative 0.67 there, and then we can calculate the intercept. How? If you just rearrange this model here, if you don't want to use that equation of a straight line to know c, that's fine. You can say y, take one of these coordinates, doesn't matter which one, just one of them, and use this value of a gradient that you just found, and this is just this line here where I subtracted nx from both sides, and to get the c, that makes c the subject of the formula, you substitute it and your c is 6.2. So now is the time that we can go back and find our original a, and value of a here is this 6.2. Log a is 6.2. So we're going to match log a with 6.2 and match log r. It doesn't need to be matched. Log r is x, and we can read n to be uh, negative 0.6. So we're gonna just figure out the value of a here. If we just log is this, then log means using base 10. Don't forget that. So to to get a, you need to raise 10 to the power of 6.2, and then you'll get this 1,600,000 rounded to 600,000, and you rewrite this into the original formula. These two can be used to write the for original formula, which is 10 raised. Actually, you can just put a. We don't have to evaluate it. So this way is a neater and more exact way of writing it. R raised to the power of minus 0.67. So that's it. The table of transform data to figure out the equation of a straight line, linearized model, in other words. So don't forget that here we were plotting log p against log r. So in this next example, we have given this graph where intercept is 2, and we were told that we are plotting log p against t. Notice t is not transformed here, and you have the equation of the original exponential equations like so here. So we can take log of both sides and say log p equals to log a plus t log b. Alright, if you don't know, first you break this into two logarithms, and the t as power of b there will come and sit here. So we don't need to write it there. Now we we were told that it goes, the gradient is 2. Sorry, the intercept is 2. So this log a, we can immediately write log a equals to 2. Therefore a is 10 raised to the power of 2, which is 100. And then we say, yes, the question also told us that the gradient is 0.6. Therefore t here is the variable. T is not changed, so variable is t, and constant, that leaves us with a constant here, which is our gradient. So log b is equal to 0.6, as the question says the gradient, or here constant or gradient. Alright, so I'm trying to make you understand that it is part of the x, or would have been the x-axis, therefore the gradient is the thing that is multiplied by log b. So here solving for b involves raising 10 to the power of 0.6. So maybe I didn't show you the whole question. Writing down the equation of a straight line model involves linearizing this model using logarithms, which I did by hand, and putting those values in, as the equation told us, c is 2 and gradient is 0.6 times t, and matching the right variables with the right constants and solving it. So this is what we would get for a and b, and then putting them back together. So it's part B is saying figure out the value of a and b to three significant figures. That means, well, yes, I haven't written it, but a is 100, and then putting it back into the model. Notice that the model is here log of base 10. Therefore, to get p, I'm using base 10 like so. Now, of course, that plus sign there means that I have this situation. When you have these two powers, the plus sign means that you can separate them by multiplication. Right, 10 to the power of 2 and 10 to the power of 0.6. These are multiplied. Therefore, that is literally 100 times 3.998 raised to the power of t. Okay, so that's just writing this again, the same thing. Rate 10 to the power 0.6, we already figured it out, it was 3.98. So now what are we doing here? It says parentheses interpret the meaning of constant a. Now, if you remember when we solved some initial questions, that when value of t is 0, b raised to the power of t will be eliminated as 1, so p will be a. So therefore, a is the initial value of the initial value of population. Or so the bacterial population A is 100, so the initial value is 100, rather than not 2, because 2 is the log of p, so actual value of population is this this value, not log p. All right, so I hope you had understood this, and I hope you've enjoyed this course, and I will try to make another video for the constants and using a calculator. Wish you the best.